Okay, I think we're ready to get started. Sure this is on? All right, so you had questions. Yes, yes. Okay, sounds good. All right, we're starting. Yeah, so I am recording. The paths? No. I mean, not necessarily. Okay, so the paths don't have to necessarily be equal. I mean, you can use a phantom variable whenever you want. I was talking about the fact that you might want to use the phantom variable because you want to sort of set up a model for stationarity. Thank you. That was the word that was slipping my mind. Yeah, if you want to test for stationarity, then you do need the paths to be equal, right? You would want the paths to be equal, and you would want the disturbance variances to be equal. But you don't necessarily, so yes, for station, it's like all these things, right? If you want to say stationarity, yes, you need to do all those things. But do you need to do all those things in general to fit an autoregressive model? No. And could you use a phantom variable anyway, just for kicks? Yeah, but the reason that people would often do this little trick that I showed you is because they were trying to do something with stationarity, in which case they would be, constraining the paths to be equal and the residuals to be equal. And now I can't even remember what I said for you to do in the homework. Like I might have had you try to use the phantom variable without doing a model that forces without a stationary model, just kind of so I could make sure that you could do it. I can't remember. I know I asked you to do something with a phantom variable, but I can't remember whether. Right. So it's just like to go back and fit with the other model. Okay. Yeah, you're probably like, in the vast majority of people. But really, when we talk about, just think about, I think for the purposes of right now, the easiest way to think about it is, we're talking about the stability. I call those autoregressive paths stability paths, right? And I think a couple of people asked, like, oh, when you say, stability path, whatever, when you ask about stability and reliability, what are you asking about? And stability is really about the autoregressive paths, and reliability is really about the R squared from the latent variable to the indicator. So stability is this idea of consistency across time, right? And you can sort of think about stability without necessarily imposing these much more stringent constraints on stationarity, right? So I could have a model where, well, for example, the model that we looked at last week, where our autoregressive paths were in the neighborhood of what, 0.97, 0.98, 0.99. I think it would be very fair to say that there was high stability in that model, and yet we did not actually impose the constraints that would be necessary to say that I've made the assumption of stationarity, because stationarity really says very particular things about this covariance matrix. My variances are going to be equal across time. There's going to be a pattern of my covariance matrix such that like my autoregressive paths would be constrained to be equal across time. We didn't talk about bivariate models, but if we had, then the causal paths, which would be the cross-lag paths, would be constrained to be equal across time. So like a stationary model is just a much more constrained model. And I could have high stability. I could have a very, without actually imposing stationarity. Does that make sense? And you could have stationarity actually without having high stability in some sense, right? Like you could impose all of those constraints and, you know, you could be, so to have stationarity, you would impose the constraint that the stabilities would be equal across time. However, the stabilities could be low, right? Theoretically, you could have a stationary model with low stability, you know, paths. You know, whatever. They're probably not going to be as high as they were last week. That's a fair assessment. So when I'm thinking, I mean, usually when I'm talking and when we're thinking about stability in here, we're really thinking about the stability paths, and that's really like this consistency from t minus 1 to t. Whereas stationarity is really this function of, it's like we're imposing this very stringent set of constraints on the entire variance covariance matrix. Yeah. So stationarity is really this whole, it's really about, I think it's two, it's really about this whole, it's about the whole model, it's about the whole covariance matrix, right? Yeah. Whereas, you know, we can think about the stabilities. We can think about the stabilities and just think about those paths, those parameters. And we have, you know, we can think about stability and we can think about stabilities without going, and we could even impose the constraint that the stabilities be equal across time, which would not in and of itself take us all the way to stationarity, you know, because even if we constrain the stabilities to be equal across time, if we allow the disturbances to vary across time, we've constrained the stabilities, but we haven't actually gone all the way. So it's like, I just think of it as like a very, it's just a more constrained model that we could test, that if it fits, again, there's some nice characteristics that, you know, if we can make the assumption of stationarity, then there are all kinds of things that we can do. Like, and we won't, you know, this isn't a class in time series analysis, so we're not like going to go into more depth about that really, but stationarity is this assumption that comes up a lot in time series, and you know. No, I mean, I think if you just understand that it's really about making this assumption that we have, that the stabilities are all going to be constrained to be equal and that the disturbances are all going to be constrained to be equal. And so that's really going to give us a very particular looking variance covariance matrix. I think that's fine. I don't think you really have to go more in depth than that. Sure. Other questions? Sure. Mm-hmm. I'm not sure if I totally understand your question, but yes, for this homework, you just, yeah. That's right. You're not inputting any information about means and intercepts. Yep. Well, sure. Yeah. I mean, you remember when we did growth, and we're going to talk more about means and intercepts again today in the context of multiple group CFA. But, you know, for a lot of different models in SEM, you really only need the variance covariance matrix, right? We did lots of things early in the semester where we only thought about variances and covariances. But then there are other kinds of models where you absolutely need information about means and intercepts. So, you know, for some models, you don't really need that information. And for other models you do. But sure, if you input means, if you put in a mean vector, you have more information and you can use that information. Does that answer your question? Okay. But you didn't need that information for the homework last week. So you didn't have you didn't have any mean information. But again, today it's going to be really important to think again about means and intercepts. So the first time we talked about means and intercepts was in the context of latent growth modeling. And now we're going to talk about means and intercepts a lot in the context of multiple group SEM. Okay, so ready to start with multiple group SEM? So I want to, and as requested, there are 2 extra credit questions on today's homework, on this week's homework assignment. So no, come on. You don't actually think I would do that. No, there are things like, in 5 pages or more, explain the concept of stationarity and what it means to you. No, I'm teasing. It's not that either. So, oops. All right. So actually, we don't need the first. Okay. So multiple groups. So we're going to spend 2 weeks actually talking about multiple groups analysis. This week, we're really going to focus on the measurement model. So we're going to do multiple groups confirmatory factor analysis. And then next week, we're going to sort of start where we leave off this week and assume like you've done all you need to do with your measurement model and pick up there and talk about multiple groups SEM. So, but sort of before we get started with multiple groups, let me just say that, the main rationale for doing any kind of multiple groups analysis is that you have some questions that deal with moderation, right? And there are other ways to deal with moderation, by the way. So next week, we'll talk briefly about other ways that we can deal with moderation in SEM. But we'll spend most of our time in this class sort of dealing with moderation using multiple groups. And like I said, at the end of class next week, we'll talk about other ways we can deal with moderation in SEM. But so here we're thinking, are there differences across 2 groups in terms of what? And this is what I think makes multiple groups SEM really kind of cool and exciting, but also really complicated, is we can ask, do any of our parameters, does anything vary across groups? So if we think about, let's just start by thinking about, let's start by thinking about a confirmatory factor analysis model, since that's what we're really going to spend our time today thinking about. So imagine that you want to know if 2 groups differ. Oh, and I'm saying 2 groups here, but actually it doesn't have to be. You can have more than 2 groups for multiple groups analysis. You could have 2 groups, 3 groups, 4 groups, 5 groups. I mean, at a certain point, it's going to be too many groups for you to get a big enough sample size in every group to pull this off. And B, it's just going to get really, really complicated. And so there's a point at which you get to so many groups that there are other ways to handle having that many groups, which we can briefly touch upon. But just for simplicity for today, we're going to have 2 groups and we're just going to think about 2 groups. But know that it doesn't have to be 2 groups. So if you have 3 groups of interest, that's totally fine. Okay? So think about a confirmatory factor analysis model for a second, and imagine that you are really interested in motivation. Let's say your latent variable is motivation, and you want to know, do males and females, differ in terms of motivation, or 2 groups, group A and group B. Doesn't have to be males and females. It could be any 2 groups. So do groups A and B, do they differ in terms of motivation? So, okay, that's a good question, right? I want to answer that question. And motivation is measured. Let's say motivation is a latent variable. So how am I going to do that? Well, I would want to compare the two groups in terms of their means, their latent means, right? Okay, I can do that. That's not a problem. That would be one type of parameter that we could actually allow to vary across the two groups, would be the latent means. But we kind of have to back up a little bit and say, how do I know that the way that I'm measuring motivation functions the same way, sort of, is equally, valid in some sense, right? Or functions similarly across my two groups. Maybe my measurement of motivation works differently in one group than another group, right? And if it is the case that the actual measurement of the variable isn't the same across the two groups, then it's not necessarily fair to compare the means across the two groups, right? So maybe I've written, maybe I've written a whole slew of questions with sort of one worldview in mind, and it works really well for one group of people, and then I apply it to another group of people, and it doesn't work so well, right? But I never kind of consider that, and then I just look at the means, and I'm like, hey, this group does better than this group. Well, that's not a fair comparison, right? So before we actually compare two groups in terms of, pretty much any measures, really, one of the things that we want to do is say, okay, well, does this measurement function the same way, right? Do these, and now let's think about confirmatory factor analysis for a minute and think about all of the different parameters that could function differently. So again, I think sort of before this class, you were sort of used to thinking about, oh, maybe the means are different, right? But there's so much more than that. So when we have a confirmatory factor analysis model, variable and motivation measured by 4 observed variables. All right. Marker variable. All right. Variance. So if this is my measurement model, things could vary across the two groups besides just the means on motivation. Okay, the variance. So what variance? Yes? Which variance? Yeah, okay, so the mean of the latent construct could vary across the two groups, right? The variance latent variable could vary across the two groups, for sure. What else? The factor loadings, right? The factor loadings. Or technically the measurement weights, right? Mean if the measurement weights vary across the two groups. Let's think about that. What does it mean if, so let's say that I find that in group A, well, yeah, let's say I find in group A the loading for item 4. It's much lower in one group than another. Okay, well, it probably does mean they interpret the item differently, but yeah, exactly. Well, it does mean that for sure, right? Wherever, which is lower, motivation isn't accounting for as much of the variance in that item in the group where the loading is lower as it is in the group. So motivation is a better predictor how you respond to this item in one group than in another group. Which means that this item's a better indicator, right? For, in the group in which this loading is higher. So let's think if we can, let's try to make this more concrete. So I'll give you an example. A decade ago, at least, we were doing a study with kindergarten students, and we were teaching them vocabulary words. And we had a list of vocabulary words, and we were doing some measurement work on the vocabulary words. And hindsight is 20/20. So when I tell you what the word is and how it functions, you're going to be like, why'd you even put it on the list? And fair enough. But so they were words that came from books. We hadn't totally thought about it maybe from this perspective, but so we had this latent variable, and it was sort of like vocabulary ability, right? Vocabulary ability is going to predict responses, whether or not, in this case, they were whether or not you get the word correct. Do you know the definition, right? Can you define this word? So, and we were looking at boys and girls. And it was really interesting because one of the words really jumped out when I was doing the multiple group analyses, and the word was slumber. And slumber had a much stronger relationship. So it had a much higher loading for boys than it did for girls. Why might that be? Slumber party, exactly. So girls all knew the word slumber because they knew about slumber party. And so girls, whether or not they had a strong vocabulary, could define the word slumber. But for boys, slumber was actually more related to their overall general vocabulary knowledge. So boys who had stronger vocabularies knew what slumber was, and boys who had weaker vocabularies didn't know what slumber was. But girls, whether they were strong or weak in terms of their overall vocabulary skills, they all knew what slumber was. The other word that functioned like that was bracelet. Not surprisingly. Again, pretty much all the girls knew what a bracelet was, right? So it didn't really relate to their overall vocabulary level. But for boys, vocabulary skill was much more predictive of their response to bracelet. So again, it was one of those duh-he moments where I looked at the data and I was like, well, yeah, those are bad words to choose, It was a pilot, so it was okay. This is why we pilot things, right? But it was definitely a oh my gosh kind of moment. Okay, so that's the kind of idea that this indicator might actually be much more strongly predicted by your latent variable in one group than another, right? So so we want to look and see if the loadings are equal across groups. And that makes sense because, again, if certain items function, that's one way of functioning different, for the item to function different, right? Now, remember when we were talking about growth curve models, well, and here I just said means of latent variables, we're going to bring means and intercepts back into these models, right? So not only could so we talked about the loadings could differ across the groups, but another thing that could differ across the groups would be the item intercepts. Now, I say intercepts for items and not means because, and I'm saying items, but they don't have to be items, right? These could be subscales. They're observed variables. I tend to think of it in terms of test construction because I do a lot of that, but replace item with the word observed variable, or it could be a whole subtest or test. Okay, but here, whatever my indicators are, I'm saying intercept instead of mean because all of these indicators are endogenous. So rather than actually estimating a mean for an endogenous variable, we estimate an intercept for an endogenous variable. And the intercept is the predicted value on that variable, right? So it's like the expected score when what? Well, when again, intercepts are always when everything else in the model is 0. So in this case, it's going to be when the latent variable is 0. Now, let's just assume for a minute that, we haven't talked about scaling the latent variable mean much, but let's assume we scale the latent variable mean so that it has a mean of 0, which is what we'll generally do. And we'll talk about how we're going to deal with that in multiple groups in a minute. So if I scale the latent variable so that it has a mean of 0, then the intercept is really going to be the predicted score on that indicator when you're, for a person who's at the average on the latent variable, which actually means, if you think about it, that the intercepts for these indicators should actually be the means on those indicators, right? Because I just said it's a predicted value when this is at the mean. Well, the predicted value on this when this is at the mean is actually going to be. So they're intercepts, but again, in that framework, then the intercepts are really actually going to be basically the means on those items. But they're the predicted score on the item when that latent variable is 0. Does that make sense? Okay. So now those could also vary across groups. And this is the important thing. I'm not saying that, yes, the means on the items could vary across groups. But there are sort of, if you think about it, there are 2 reasons that means on items could vary across groups. It could be that the means on the items vary across groups because the 2 groups differ in terms of their overall amount of this trait that we're measuring, right? So the 2 groups differ on the latent variable. And so imagine, obviously the 2 groups differ on the latent variable, then the 2 groups are going to differ in terms of what their scores on the indicators are, right? That makes sense. But a more interesting question, I think, is, do the 2 groups differ in terms of their score on the indicator, holding constant or controlling for their overall level on the latent variable? So whatever difference I might observe between the 2 groups on that item or on that indicator, it isn't a function of one group being higher than the other group, because I'm controlling for overall groupability, but really it's a function of, you can think about it as if you took 2 people who had equal ability scores or equal scores on the latent variable, and you asked them this question: would the people in one group score higher than the people in the other group? And if the answer to that is yes, then that's one type of differential item functioning that we're often really interested in. That's a problem, right? Another type of differential item functioning is actually that the loadings differ. That's also problematic. But it could be the case that loadings are the same. So the items are sort of equally, the latent variable equally picks the item score across the 2 groups. But it could be that the intercepts are different, which suggests that, after controlling for after controlling for whatever it is, the latent variable, that one group is doing better on a given item than another group. So, okay, I'll give you a couple examples. Well, this is not the best example because I just said that I just mentioned that the loadings differed across the 2 groups. But going back to the example of bracelet and slumber, which group do you think had higher intercepts on slumber and bracelet? Girls, exactly. Because as I said, girls could define those 2 words sort of almost no matter what their score, what their sort of overall vocabulary knowledge was. And so those items were both less predictive. So they had different loadings, and they had different intercepts. They had higher intercepts and they had lower slopes or lower loadings. But again, you could imagine a situation where an item might be equally predictive, but you still might see a difference between two groups. So, I don't know, anybody have a good example? Yes. Like if you're like the MC of an award show, for example. No, just kidding. But yeah, no, well, actually, there is a kind of an interesting example that I know that I was reading about. So in IQ testing, there's this section of the test that's called like comprehension on one of the tests. And it's sort of about, there's a little bit of like social norm stuff. Like what should you do if you, I don't know, see somebody getting robbed? I'm making this question up, but like, what should you do if you see a crime being committed, right? And, interestingly, kids from different contexts might not answer that. The right answer is like, oh, you should call the police, right? But in certain neighborhoods, you try to avoid calling the police under any circumstances. Like police are kind of like maybe not considered to be your protectors, right? So you can imagine that, there might be kids who otherwise are scoring really, really well on the comprehension section, but don't say, oh, I would call the police. That might be the last thing they do, right? And so they might score lower on that item even after controlling for their overall ability level. And it's really sort of a function of like the neighborhood that they live in and their lived experiences, right? So that could be, and it might not actually, so it could end up, often it ends up, but sometimes that ends up then also being less predictive. It makes sense. But you could find a case where the loadings are equal across the two groups and the intercepts differ, right? Yeah, I know. And that's where I'm having trouble, because like often when I think of good examples where the intercepts differ, it feels to me like the loadings would differ too. But well, it can often be the case that they go together. What I will say is you actually don't want to test to constrain the intercepts to be equal unless you can constrain the loadings to be equal. So as I'm describing, we're sort of just talking about all the things that can vary right now, but we're going to talk about how systematically you're going to kind of go through a set of models to look at this. And the first thing that you're going to do is constrain the loadings to be equal across the two groups. And if you can constrain the loadings to be equal across the two groups, then you can look at constraining the intercepts to be equal across the two groups. But if you discover that you can't constrain the loadings to be equal across the two groups, for any indicator where you can't constrain the loadings to be equal across the two groups, you're never going to try to constrain the intercepts to be equal across the two groups, right? And in some sense, it doesn't even make sense, right? So the loadings are like slopes, right? So how could you constrain the intercepts to be equal if the slopes are varying? So they often will go hand in hand, but it is possible that you could find that you could constrain all the loadings to be equal, and then there's some, one or more intercepts that you can't constrain to be equal. And I've definitely seen this happen. I just can't think of a good obvious example that everybody would be able to relate to. So the next thing, right, are these intercepts. And intercepts are really Peter means holding constant a latent variable. And what we're going to do is we're going to hold constant that latent variable across the two groups, which really means that we're comparing those means the same, like for you know, people who are at the same level on the latent variable, which is very different from saying that the means differ across the two groups. Because I mean, it could be the case that all of the means differ across the two groups because the one group is just higher than the other group. And if all, you know, but what we're really saying is like, yeah, no, after controlling for the overall level of motivation, this item, you know, this one group has a higher score on this item than the other group, which again suggests that that item's functioning differently for one group than another group. So, okay, so we could have the loadings could differ, intercepts could differ. And then finally, we have our errors. I mean, honestly, I feel a big sense of success if I can constrain all of the loadings and all of the intercepts to be equal across the two groups. Yeah. But the final and sort of, you know, I suppose most stringent test would be that the measurement errors could also be constrained to be equal across the two groups. So what does that mean? This is also maybe the hardest one to kind of think about a little bit, but what does that mean? Well, what does it mean if I can't constrain them? Yeah, it means that this error variance is bigger in one group than another group, right? But I've constrained the loading to be equal. So how, you know, what's one way you could get errors to be different in, let's assume that really that sort of the latent variables equally predictive in both groups. What would give you bigger error variance? I mean, remember that the variance in the item or the indicator is explained by proportion. There's this amount by the factor, and then this is just the unexplained piece. But yeah, that's what I was gonna say. So one reason that you might find that you can't constrain the error variances to be equal across the two groups is because there's just more variance in this item in one group than another group. So the variances in the indicators aren't equal. So there's more variability in one group than another on that particular indicator. Right? And actually, if we want to establish equal reliability across the two groups, then we really would like to be able to constrain these error variances to be equal across the two groups. But again, this is like for researcher developed measures, this is like a steep hill to climb. For commercially developed measures, you know, less so, right? But like if you're developing your own scale to use in your dissertation, and you actually are able to constrain all the loadings and all the intercepts to be equal, and you discover that like a couple of the error variances differ across the two groups, like, you know, I would call that a success, honestly. That's pretty good. So we can constrain these error variances to be equal across the two groups. This is where we're going to be maybe a little bit more forgiving in terms of, you know, again, optimally, we'd like to be able to constrain all of the error variances to be equal across the two groups. But, you know, if we can't, like, okay, maybe we can live with that a little bit better than the loadings and the intercepts, right? Because again, you know, if there's more variability, I mean, what does it mean if there's more variability in an item for one group than another? I mean, that's kind of an interesting, again, that's kind of an interesting thing, right? And, you know, how much, like, there are these questions, how much more variability? Is it like, this is the other problem, because how are we going to make all of these determinations? Well, we're going to use chi-square difference tests, right? Those are going to be somewhat a function of the sample size. Again, there are other ways that you can compare models across groups. You can look at fit indices. We'll do that too. But, you know, with a large enough sample size, even trivial differences in terms of those error variances might end up sort of looking important, and maybe they aren't. But like if there are huge differences in the variance of an item, I mean that could actually be important, right? Like why is it that, and I would argue if there are huge differences in the variance of the item, that is actually likely to maybe end up playing out in terms of not being able to, but not, I mean maybe not always, because these are different things. Yeah. Sure. Sure. Mm-hmm. Yeah, I mean, I think that's a really good point. Maybe I have two groups, and maybe the one group is just more variable in terms of SES and lots of things that might actually influence whatever the latent variable is, and the other group is more homogeneous, right? And so, absolutely. And so I might find then that, okay, got these items, they seem to be effective across the two groups, right? I can constrain these loadings to be equal across the two groups. Intercepts to be equal across the two groups. So it seems like after I control for the level of the latent variable, items seem to be functioning in the same way across the two groups, but maybe I fall apart here in terms of the error variances, because you know the one group is just way less homogeneous than the other. And I would totally, now, you can also find also do have latent variable variances. Won't necessarily, so there are sort of two places where there could be variability that differs across the two groups. One is in terms of measurement error variances, which case that's the piece of variability in here that's left over after controlling for the factor. The other place that we might actually find differences, variable variance. So it could be that one group is just way more variable on motivation than another group is, right? So find that the latent variable variance differs across the two groups too. And for that matter, two places where we're looking at, right? So we talked about the intercepts, but it can be the case that the two groups vary in terms of their means on this latent variable, right? So these are all the places where groups can differ. There are a lot of places where groups can differ, right? They can differ in terms of relationship between indicator, in terms of the level on the indicator, the latent variable. They can differ in terms of the amount of error, measurement error, which is really that unexplained variance after controlling for the latent variable. They can differ in terms of the variance on the latent variable, and they can differ in terms of the mean of it. The logic is that we don't really know about whether they can differ in terms of the latent variable until at the very least we can show that the items are sort of functioning in the same way across the two groups. Otherwise, it's like comparing apples and oranges. Like, does not make sense to figure out whether the means differ or the variances differ on the latent variable if the latent variable is essentially not functioning the same way across the two groups, which suggests that it sort of means different things, right, in those two different groups. And so in that case, it's really not, wouldn't really be fair to just kind of compare across the two groups. So, yeah. No, so what we're going to do, I mean, we're kind of jumping ahead, but what we're going to do is when we get into the multiple group scenario, we're going to have the latent mean in one of the two groups be 0, and we'll allow the latent mean in the other group to vary. Because if we constrain the latent means to be equal across the two groups and they really are different, then we're going to find differences in other places, right? So what we need to do is constrain the latent mean to be 0 in one group, allow it to freely vary in the other group, and then a mean of 0 is going to, a latent mean of 0 is going to kind of mean the same thing across two groups. It's going to mean somebody who has a score, a latent, like it's not a score because it's latent, but somebody who's at the latent mean or at the latent 0 point, which means they would be sort of at the mean in the one group, and it means they might be slightly above or slightly below the mean in the other group. But we're still they're still at that level. Yeah? Sure. Yeah, it does presuppose that both groups, unless you were interested in looking at something as a function of time, like I could imagine a scenario where maybe somebody says, I've got data from a decade ago, or I've got data on kids pre-COVID and post-COVID, and I want to see if these things function the same way. So if it's part of your research question for time to be the thing that's changing, so I've got a sample from 2019 and a sample from 2022, and I want to see if my instrument works the same way, you could do that. But often what we have is sort of, we've got two particular groups of people that we're interested in, two different populations or two different subpopulations that we want to compare, and we want to make sure that it's sort of a fair comparison before we move forward. Although, again, as I say, there's a lot of work that's going on. There's a lot of work that's going on in terms of trying to figure out what's similar pre and post COVID, right? So. Oh, yeah, I see what you're saying. So could I have the same set of kids? Yeah, I'm thinking of this as being different groups of kids. Yeah, I don't think, I was going to say, if it were the same group of kids, the way that I would model that isn't with multiple groups SEM, but what I would do is I'd have, you could do something. I've got motivation. Really, I have these measures again because it's the same kids, and I would think kids' motivation in third grade would be related to their motivation, right? Now, it doesn't mean all of a lot of the techniques we're going to talk about. What you could do, again, it's not a multiple groups all in the same model, but you could still say, hey, these are the same variables. I've asked about the same motivation questions. I want to know, can I constrain these? That's what people measurement done. It's not done in a multiple groups. But the rest of what we're talking about actually comes into play. I don't know. Could or could not constrain. You might be able to make a case for why you might think that different because maybe I don't know, right? Or you can constrain, but again, you constrain the and it makes more sense to look at how the means. Don't constrain the you can't really look at. You would want to. You would. Well, so the big difference is everything is all on the same model here, right? Whereas what I'm saying with the other one is same model twice in two different groups. So a poor man's version of multiple groups analysis would be I have two data files. I run my CFA and this is what people used to do, by the way. I run my CFA and you could do this too. Honestly, I do poor man's multiple groups sometimes just to get myself on the board and see what's going on. So poor man's multiple groups would be I run the whole model in this sample and I run the whole model in this sample and I compare the parameters across the two samples. I've run the same model two different times, right? Whereas over here, it'll all be contained on one model with one group of students, but I've got these constructs across time. Could be. Could be. I mean, right now, yeah, it could be, but I mean, the way I've drawn it, these will be statistical. From the structural perspective, I have a correlation, or I have, but you're right that like motivation in third grade, fourth grade, then I could be asking if I have an autoregressive. Yeah, absolutely. Autoregressive. Okay. There was something else. Oh, I know what I was going to say. Just, I'm not going to have a lot of time to do longitudinal. You know, it's so sad. I don't think you're probably sad. You're probably sick of me already. But like, you know, if we just had like 10 more weeks, there's so much more we could do in this class. No? Yeah. Yeah, you're like it's like when I try to do algebra with my kid, and they're like, do you have any math homework? Do you? Jess is just like, but since we're not gonna have time, so what constraint folks to be generally constrained errors. But the important thing that errors to be equal. The other thing that you would often do though, actually build a correlation. To V2 and E. So you would often correlate the errors of the same item across time. And if you think about that, that makes a ton of sense, right? Because what that's saying is, you know, this item, people's responses to this item in third grade and the exact same item in sixth grade, I'd expect this error correlation or covariance to be positive, and that would be saying like they're more similar to each other than would be predicted by the factor model. But that makes total sense because it's the exact same item that's actually taken across those two grades. So that's like one difference, besides the fact that it's all like one model with one set of people. But another big difference with longitudinal invariance is that you're often going to allow the same item to have a correlated error across time. And you're going to do that a priori. So remember, I've given you all kinds of like caveats about not like, you know, p-hacking your models too much, right? But like, if I were fitting a model like this, I would go in a priori. I would say, you know, I totally expect the item that I'm giving in third and sixth grade to be more correlated with each other than would be predicted just by their joint correlation with motivation, right? And so you could even, you know, pre-register that. If you were pre-registering the study, you would say, and I'm going to correlate the errors of the same items across time. And that's really, really common in longitudinal measurement and variance studies. And you're unlikely to get good fit if you don't do something like that. And I don't know if you remember, but because I didn't make a stink about it at the time, but when we did the mediation example way back when, and there was a pre-test latent variable and there was a post-test latent variable, I actually correlated the algebra subtest at pre and the algebra subtest at post, and the geometry with geometry and the measurement with measurement. So I did actually do that. It's really, really common. So this is a good example of where like correlated errors make conceptual sense. It's not just like mucking around. Okay. Any other questions before we move from the first slide? Wow, we're still on the first slide. Well, we've covered a lot of stuff though, so we'll keep going. So anyway, the point is, what I was saying was we're doing moderation. This is one way of doing moderation, but we're doing moderation with some sort of categorical variable, two or more groups, right? We're not going to use multiple groups if our moderator is a continuous variable. So that's next time I'll talk about how you can deal with continuous moderators in SEM. But, you know, often our moderators are categorical. So multiple groups works really, really nicely. All right. Yeah, I already said that. Okay. So our basic logic is going to be, we're going to force, we can constrain, we can do these cross group equality constraints. So we can force the same. And when we do these equality constraints, we're actually going to be constraining the unstandardized estimate of the parameter to be equal across the samples. So, and that's an important point. So, you know, that's true anytime we do these things. When we constrain to, you know, we constrain these two paths across the groups, we are actually constraining the unstandardized coefficient to be equal across the two groups. And what that means, by the way, is that the unstandardized coefficient could be the same and the standardized coefficient could be different. And why might that happen? Well, it might happen if either of these variables, then the standardized loading will not be the same. And so often often what you'll see is that the standardized loadings are a little, they're sort of trivially different, right? Which is not necessarily something you're going to be super worried about. If they were, you know, radically different, but, you know, again, that could happen. That's something I would think about a lot more, because that would suggest to me that my variances are so different that, again, I would conceptually want to kind of dig into that. Yeah. Mm-hmm. Yeah. No, anytime you're putting equality constraints, it's always on the unstandardized. And then the standardized so those are sort of our parameters, or whatever the unstandardized parameters are. And then the standardized is really just a scaling of the unstandardized using the variances, you know. So yeah, so anytime you're constraining on the unstandardized. Okay. Which, by the way, means that it's not the only reason, but we're going to want to use a marker variable strategy when we do measurement invariance. You know, one important reason is what happens if we use a fixed factor variance strategy? Like, at first you might be like, oh, I should use fixed factor variance strategy because then my unstandardized parameter estimates are the same as my standardized parameter estimates, right? So then if I constrain the loading to be equal, I'm constraining the standardized loading to be equal too. But what's the problem with using a fixed factor variance strategy across two groups? Well, what do I do with a fixed factor variance strategy? I fix the variance of the latent variable to be 1, right? So I'm fixing the mean of the latent variable to be 0 and the variance of the latent variable to be 1. And let's just think about the variance for a second. What would be the problem there? Yeah, I'm forcing the two groups to have equal variance, right? So I'm forcing the two groups to have equal variance in terms of the latent variable, which isn't necessarily, you know, that might be something I'm actually really interested in. And that isn't necessarily a good idea. It's quite common for two groups to differ in terms of their variances on the latent variable. So if I use a fixed factor variance strategy, I'm forcing the two groups to have like equal variances, which is bad. So I definitely want to use a marker variable strategy. But okay, what's it's not a downside, because we're going to use the marker variable strategy. But now, remember before I was like, it doesn't really matter. As long as you don't pick a total dog of a marker variable, you're fine. Well, now it matters a lot more. Why? Why does it matter a lot more what's my marker variable? Yeah, exactly. Like, I am in trouble if I pick slumber as my marker variable. Because what I do if I pick slumber as my marker, because you're going to use the same marker variable across the two groups. Clearly, it needs to be the same item, right? And remember, with the marker variable, we're constraining that path to be 1. So if I constrain the path to be 1 in this group and in this group, I am actually constraining the unstandardized loadings to be equal for that one item, right? So I can't actually test whether there's a difference on that item. It's sort of like an anchor item in some sense, right? So and if I pick an item where it's reasonable to make that constraint, that's great, right? And then everything works well. But if, let's just say I pick the one item, like slumber, and all the other items actually do look good, they could be constrained to be equal. But if I constrain the two, if I constrain the item to be equal, that is the one item where they're really, really different, and I force them to be equal, what do you think is going to happen to the other items? Are they going to look good anymore? No, they're going to, right? I've like forced these two different things to be equal. And so now actually things are going to look bad for the other items. So it's really important you pick a good marker variable. Yeah. Maybe they won't look quite as bad, but but it'll be problematic. It'll be problematic, and you won't be able to constrain the loadings for the other items to be equal without having problems. And the problem isn't really the other items, the problem is the marker variable that you chose, which, by the way, is one of the reasons that I sometimes run a poor man's multiple group CFA, right? Or I'm going to actually show you, another solution to that problem that doesn't involve actually running two different CFAs. But one of the first models that will fit actually allows all of the loadings to vary, well, except for the marker variable, right? But if you find that all of the other loadings look really different, except for your marker variable, then you choose another marker variable and you rerun it, right? So like, if it looks like all the other, could be you pick the right marker variable and everything else is really different, or it could be you pick the wrong marker variable and you just need to pick a new marker variable. But I mean, I do think about it a priori, but sometimes you're just wrong, right? So like, a priori in retrospect, I would never pick slumber as the marker variable, right? But you might not totally realize your mistake until you've run. Sometimes hindsight is 20/20 on things like that, and as soon as you run it, you're like, oh crap, I should not have used slumber as the marker variable, and then you go back and you use a different marker variable. And remember, these models are statistically equivalent, so it's really not a big deal to choose a different marker variable. Like, and again, a lot of times it's not really going to matter which you choose as a marker variable, but if you've got like one item that's really different across the two groups, that is not necessarily the item that you want to pick as a marker variable, right? It's not necessarily. It's not the item you want to pick as a marker variable. So now, which item we pick as a marker variable matters. Yes. So would I pick an item that has like similar distribution across the two? I mean, yeah, sure. I mean, that seems like it might be good. That might, again, there's no guarantee that means that it's going to be a good marker variable, but I mean, all other things being equal, having similar distributions does seem good. I mean, when you say similar distributions, I'm assuming you mean like the mean is pretty similar, right? They're sort of distributed in similar ways. Again, like, that's not a guarantee, but I think would be a very good empirical strategy to sort of look at which item might be a good marker variable, right? And also, I mean, again, if you've looked across if you do happen to run this across the two groups, you might have a sort of a sense of which items are functioning differently across the two groups. You can also look at the pattern of correlations, right? And you can look at the pattern of correlations across the two groups. If there's one item that seems to be really a lot more correlated with the other items in one group and a lot less correlated with the other items in another group, that might be an indicator that the slopes might end up being different across those two groups. So I think there are lots of things. I like that though. I like looking at the distributions. I think that's a good idea. Again, not a fail-safe guarantee, but I think a really smart move. So, okay, so what we can do is we can start with a completely unconstrained model. Now, the unconstrained multiple groups model is not, it's going to be as unconstrained as it can be and still be identified, right? So for example, we have to have a marker variable to be identified, right? There are these things that we're going to have to do to be identified. But we're going to start with the most unconstrained model that we can, and then we're going to make a set of increasingly strict constraints and look to see, does the model fit get worse as we make those constraints? So we start with like a model that's as unconstrained as possible. And that goes well, we'll constrain to be equal. And then if that goes well, we'll constrain the errors to be equal. And then finally, we can constrain, the means, the latent means and variances to be equal. But again, I sort of think of measurement parameters, where in some sense these are more, sort of conceptual or structural parameters, right? Like it's not a fail necessarily. If we constrain everything else and the means end up being different, well, then we have established the invariance of the measurement model, and we found that these two groups differ in terms of their, right? Or that these two groups differ in terms of their variances. So in some sense, this sort of becomes, in my mind, sort of brings us into maybe what was the conceptual question you were interested in answering in the first place once we get up here. But this is like, okay, but we need to really establish that this instrument or this measurement model is functioning the same way across the two groups before we even ask the question of whether the two groups are different or not. All right, so we're gonna do this with a set of chi-square difference tests. Again, with the caveat that seems to work pretty well in moderate size samples. If you have ginormous samples, then obviously chi-square difference test is going to probably be too sensitive, and looking at differences in fit is a good idea. And there are some papers that talk about sort of looking at sort of degradation in fit measures, and we'll talk about that too. Okay, so back to means and intercepts. Okay, I think I don't have to say anything about this slide. We're going to think about mean structure again. So here we go. So how many means and intercepts are in this little picture? Okay, one latent variable mean, right? The factor mean, how many intercepts? 4 intercepts, right? So we've got 1 mean and 4 intercepts. How many actual pieces of mean information do we have? 4, right? So in this simple little model, there is no way to actually estimate the factor mean and the 4 item intercepts or the 4 indicator intercepts, right? So again, in a normal single group kind of a scenario, what's really commonly done often is to just constrain, because the factor has no real scale of its own, the mean of the factor is just constrained to be 0, right? And that works fine in a single group kind of a scenario, and then we estimate all of the item intercepts. But in a multiple group scenario, we actually want to know if the latent mean is different across the two groups, right? So we don't want to constrain both of the factor means to be equal to 0. That would be problematic, and sort of it might actually cause our measurement model to sort of get a bit warped. Hold on one second. My husband is home. We're getting a new dryer. I just want to make sure it's not it's Norwich. Hello? 30 minutes. Okay, great. Now I know that and he doesn't, but that's okay. That's exciting. Our dryer broke over the weekend. It's very stressful. Anyway, so back to means and intercepts. Okay, so in a single group model, I'll often just constrain the factor mean to be equal to 0. But now imagine that I have a multiple group model. So I don't want to constrain the factor means to be equal to 0 necessarily. Well, I don't want to constrain both factor means to be equal to 0. So if you think about a multiple group situation, how many mean pieces of information would I have? I have a mean for each group, right? So if I have 2 groups here, I would have 8 pieces of mean information. The means on, x1 through x4 in group 1, and the means on x1 through x4 for group 2, right? So, okay, so great. So I have 8 pieces of mean information, and I need to estimate the means and intercepts for my model. So what could I do? Any ideas? Yeah, so one strategy is I can use the marker variable, and I can constrain, I already constrained the loading of the marker. So again, I'm putting faith in this marker variable. This is a good variable to constrain to equal across the 2 groups. I'm kind of sunk if it's not, but making that assumption and moving forward, I can constrain the intercept for the marker variable to be 0. So now I'm constraining the loading for the marker variable to be 1 and the intercept for the marker variable to be 0. Yeah. Well, I have 8 pieces of mean and intercept information for my 2 groups. So I can only estimate 8 pieces of mean and intercept information, but I have potentially 10 things I would like to be able to estimate, 2 factor means and 4 intercepts, right? So 8 intercepts and 2 factor means, which one for each group really, like 5 pieces for this group, 5 pieces for this group, but I really only have 4 pieces of information for each group. But if I take it all together, I've got 8 pieces of information. Those are my knowns. There are 10 potential things I might want to estimate, but I can't. So I'm trying to think about what would be some strategies that I could identify this model. So, and there are a couple of different ones. So the first strategy is exactly what we just said. I can constrain the marker intercept to be 0 in both groups, which means, that that means that the latent variable is really going to be sort of scaled as in the metric of the marker variable. Okay, fine. It kind of was already. And that's fine. That'll work. That works. So that's what's called like the marker intercept strategy. And now if I do that, I'm estimating 3 intercepts, right? And I can now estimate both latent means, freely estimate both latent means. So I don't have to actually constrain either latent mean to be 0 because I've constrained 1 intercept in each group to be 0. Does that make sense? Okay, that's option 1. Option 2 is, hey, maybe I want to constrain, I could constrain the mean in one group to be 0, the latent mean. Because again, there's no obvious metric for the latent mean. So I could constrain the latent mean in one group to be 0, and I could allow the latent mean for the other group to freely vary. Well, okay, so that's one degree of, that's one constraint, right? So if I did that, right now, I'm trying to estimate 9 pieces of information, or 9 parameters with 8 knowns. So I still need to do something else. So that something else could be, there are a couple different ways I could do this. I could constrain the marker intercept to be 0 in one group and allow it to freely vary in the other group. Or I could constrain the marker intercept to be equal across the 2 groups. And either of those things actually buys me that extra degree of freedom, right? You think about it, because if I constrain the two intercepts to be equal to each other, then I'm only estimating one intercept for those two, for those two groups, plus I'm estimating the one mean in the one group, plus I'm estimating these other 6 things. So that'll get me to my 8. Or I could use that marker intercept strategy in one group and constrain the marker intercept to be 0 in one group and allow it to freely vary in the other group. Any of those things will work, by the way. The important thing is that I've got to make sure that I can't go over the 8. I got to make sure that whatever I'm doing is identified. So, yeah, I just said all of that. And again, I'm just reminding you, you really have to think about the identification of the mean structure separately from the identification of the variance covariance structure. So it doesn't matter if your model has 57 degrees of freedom already. You really just got to narrow in, you got to zoom in on the mean structure and make sure that you're identified in terms of the mean structure. All right, and then just a kind of a reminder. So whatever we do, any of those strategies that I just described are actually going to give me a just identified mean structure, right? So I could, because I'm estimating 8 pieces of mean information, and I have 8 pieces of mean information. So in any of those scenarios, the mean structure is not contributing to the misfit of the model at all. And it doesn't matter which way I identify it, because I've got, I'm estimating 8 mean and intercept parameters, and I've got 8 pieces of information, the mean structure is just identified. So I can totally reproduce those 8 means in any of those scenarios that I just described to you. And so in general, when we're fitting mean structures, not in growth models, obviously, but most of the time when we're doing stuff in SEM and we have means, we're fitting just identified mean structures. So the mean is not, the mean structure is not actually contributing to the misfit of the model, which is why we could kind of ignore that whole thing in the first part of class. Okay, so again, I said option 1 was, we can set the intercept, right, for one of the variables to be equal to 0 across the 2 groups. We already talked about that. And option 2, as I said, we could, constrain the latent mean to be 0 and freely estimate all of the intercepts. Oh, well, actually, I'm ahead of this, right? That's just in a single group. But in the multiple groups, as I already said, we can use this marker intercept approach or this reference mean equals 0 approach. So in the reference mean equals 0 approach, we can fix the factor mean in the reference sample to be 0. We estimate the factor means in all of the other groups. So when I say samples, I'm talking groups. And then the important thing here that's really nice that I hadn't said before is if I do that, then if I constrain the factor mean to be 0 in group 1, but I freely estimate the factor mean in group 2, what I'm actually going to get for the factor mean is basically the difference on that factor for group 2. So let's say I do this and I fix the factor mean in group 1 to be 0, and the factor mean in group 2 is 0.5, let's say. That means that group 2 scores again, I hate to say scores because it's a latent thing, but group 2 is 0.5 higher on the latent mean than group 1 is. And the nice thing about that is that we actually get a test of statistical significance for every parameter in our model, right? So remember that, we actually get a critical ratio for the latent mean. So that point, I get this 0.5, and we'll talk about how we can get an effect size for that in a minute, but I get this thing that says 0.5, it's 0.5 standard deviations higher, or not standard deviation, sorry, it's 0.5 higher in group 2 than group 1. if I look at the critical ratio, if I look at that z-score, if that is statistically significant in group 2, because this group 2 thing is now really the differential between group 2 and group 1 on the latent mean, if that's statistically significant, that's actually like a t-test using latent means. That's really what it is. It's just giving you, is the difference between the two groups on this latent variable, is it statistically significant? And so that, in my mind, is one of the big advantages of using this reference mean of 0 approach, because I actually then get a statistical test of the difference between the two latent means. It falls right out of my multiple groups analysis. Yes, Hannah? Over something important, hold on. On slide 9, I can't. Slide numbers. Okay, hold on. Let's see it. Well, this is all, so this, I skipped over it because this was all like assuming you had a single group model here. So assuming you had a single group model, forget it, I was sort of working us up to multiple groups, but we'd already kind of worked our way up there. So I was saying, like, in a single group model, you could either set the intercept of one of the variables to be 0, or you could fix the mean of the latent variable to be 0. And that's true. And actually, the default in M+ in a single group model is to fix the mean of the latent variable to be 0 and to estimate all of the intercepts. So that, well, so like we've always referred to the marker variable as the variable where we're setting the loading to be 1. And I'm just saying, if you're going to set the intercept of one of the variables to be 0, use the same variable that is your marker variable. Yeah, because it's not going to happen by default, because M+ by default in the single group case is just going to fix the mean of the latent variable to be 0. But if you want to, for some reason, in a single group analysis, or once we get to multiple groups, if we're going to use this strategy, we don't want to be like mix and match and have like, oh, this be the marker variable for the loading, and I'm going to use this be the marker variable for the intercept. That would be weird, right? So all that one means is, like, if you're going to use whatever, if you're using a marker variable strategy for factor loadings, it makes sense to use the same variable for the marker intercept if you're going to use that strategy. Just put it all on one variable. Don't like have it across different variables. That's all I meant. Does that make sense?
Yeah.
Yeah. Sorry. Okay, so really annoying. Right. So yeah, so this is what I was saying. The statistical test of the latent mean for the freely estimated group tests the difference in the latent mean between the two groups. So it's a latent variable t-test, which is so cool. I mean, in some ways, like, man, you mean I got to this point in the semester and we're talking about t-tests? But it's not just a t-test, it's a latent variable t-test. So it's cooler. All right. Yeah, so in terms of measurement and variance, again, okay, I didn't talk about this. So it could be the case, as is so commonly the case, you might find that you can't constrain all of the loadings to be equal or all of the intercepts to be equal. And so then the question becomes, well, how problematic is it if there's just one item that varies across the two groups, right? And so, there's this whole sort of literature on partial measurement invariance. And the idea of partial measurement invariance is I can constrain a bunch of the loadings to, or a bunch of the parameters to be equal across the two groups, but I can't actually constrain all of the parameters to be equal across the two groups. And again, like, how much of a problem is this? Well, it's in some sense depends on how much of a like how different are those parameters across the two groups? How many parameters do you need to allow to vary across the two groups, right? Certainly, and again, I think there's more sort sort of acceptance of this idea of partial measurement and variance in the world of sort of researcher developed measures for, you know, research studies, right? Versus like commercially developed measurement, right? So partial measurement and variance doesn't fly if you're developing an IQ test or an achievement test or something that's going to be given, you know, something you're going to commercially market. You can't be like, most of the items work the same way across the, a few of the items are non-invariant. No, you can't do that. But like, again, if it's your dissertation and you've already collected the data and, you know, you discover that one of the items out of your, you know, 15 items or whatever doesn't function exactly the same way across your two groups, you probably don't want the answer to be start over, right? You probably want to be able to do something. And the answer there, honestly, is, I mean, I think there are two potential answers, which we're not going to, you know, we're not going to get into this today. But answer one is, yeah, exactly. That's what I was going to say. And that's the part we're not going to get into today. Like that could be, right? We could have a whole conversation about like, is it better to delete the item or leave it in and allow it to freely vary across the two groups? And, you know, what are the pros and cons, blah, blah, blah. But one option is legitimately, and especially if you've got a whole slew of items and you find that just one is invariant, you know, maybe that was just a really terrible item. Like the example I gave about the, you know, what should you do if you see, you know, crime being committed or whatever. Maybe you look at it and you're like, man, I got 24 other items and they all function well. And now that I think about it, this item's really kind of biased against particular groups of people. I should just throw it out. That's legit. But you know, the other option is to just allow the item to vary across the two groups, which really means, if you think about it, if let's just say I've got this item and I allow the loading and the intercept to vary across the two groups. Well, now I'm sort of defining the variable slightly differently across the two groups, but I'm still going to do a better job. I'm going to get a better information up here. I allow that item to actually be differentially predictive across the two groups than if I constrain it to be equal. Right? So if you find an item really isn't functioning the same way across the two groups, you either delete the item or you allow the item to function differently across the two groups. And you should get better, you know, it is better not to constrain an item to be equal that should not be constrained to be equal, basically. You should not just be like, whatever, I'm just going to pretend I didn't see that. Yeah. I know, isn't that a shame? Because they haven't taken this class? No, I mean, in seriousness, I think, why do people not do measurement and variance studies? I don't know. There should be, I think there are, okay. How jaded should I? Well, yeah, people, right? We know that first, I do think things are getting better. Like in general, I look at the state of research now versus 10 years ago. I mean, I know you're young and idealistic and it probably looks like crap and I still see a lot of crappy stuff, but I got to say it's less crappy than it used to be, you know? So that's good. So I mean, first I think we are moving in a direction where people are doing more of this work, and that's good. But you're right that we're not doing enough of the work. And now I'm going to be really sort of cynical and say, I think part of the problem is that this work is not necessarily easily publishable on its own. And sometimes people just want to do what's going to get them the publication. So like, if you think about it, let's say I've got an instrument and I'm going to do this measurement and variance study. And I discover that it's actually probably more publishable if you find invariance, obviously, right? If I can take this instrument that people are using and I can show that it is invariant, you know, across different racial ethnic groups or across different, you know, English learners and non-English learners or whatever, that's a good thing. It's still an instrumentation piece, and sometimes those are hard to publish in and of themselves, but it's a good finding. So people be like, yay. So maybe it'll get published. But if I do that same work and I find that this instrument is non-invariant, I think it's even harder to publish that, because basically you're saying, here's this instrument somebody created, it's not that great. And I just think it's hard to convince editors sometimes to like publish a paper like that. And so I do think that because some of these things are harder to publish, that maybe some people aren't engaging in that work. Is that a horrible thing? I don't know to say. Like, but I think that's kind of true. I think we need to do more of this. And I think that when you get out in the world, you need to hold your colleagues, responsible for actually doing this work, right? And so it's up to reviewers to say, hey, you're comparing the means of these two groups on this variable, but how do you even know that these means are comparable? Have you done that work, right? And more people need to say that. And I think if people are held accountable for having done this work before actually the mean difference stuff is published, then people will do it because they'll have to. But right now, I don't think people are being held accountable for that. The other thing I will say is that, it takes a pretty big sample to pull this stuff off, because, SEM is a pretty large sample technique. And if we're going to be looking at the differences between these two groups, we're now going to need a decent sized sample in each of the two groups. So, where I needed like a couple hundred before maybe to get on the board, now maybe I need a couple hundred in each group to get on the board. So that's substantial, right? One of the things I struggle with is, often even when you want to do this work, it's not always so easy to do it for everybody. So like, for example, you might have a sample and you might have 1,000 people in your sample, but there might only be, I don't know, 10 Native Americans, let's say. And the reality is, with 10 Native Americans in your group, you have more parameters you would potentially be constraining than people in that subgroup. There's no way to do a measurement and variance study to see if these items function similarly for Native Americans if there are only 10 Native Americans. So I think that's also part of the problem, is that we often, like, again, it's not an excuse, but like we often maybe don't have a large enough sample with with some particular groups to do that work. So I think those are all, reasons, but you're right, it needs to happen. So, all right. Yeah, I already said that. Okay, so we're gonna fit a series of increasingly constrained models. We're gonna favor the most constrained model that provides good model fit. We can use chi-square difference tests to compare these increasingly constrained nested models. And remember, as you think about it, as we make these sets of constraints, we are getting nested models, right? Because remember, nested, if we're sort of going from, we're making an increasing set of constraints, right? Those models are going to be nested. So, the unconstrained model is going to be nested within the model where we constrain the loadings. The unconstrained model, by the way, is usually the first model we start with. And then when we constrain the loadings, we call that the metric model. The sort of metric invariance means you've constrained the loadings. Scalar invariance means that you've constrained the intercepts. So we'll often start with a totally unconstrained model, or as unconstrained as we can and be identified. Then we'll go to a metric, and then we'll go to a scalar model, and then we can constrain the error variances. So here's the taxonomy of measurement models that I'm going to suggest that we use. You'll see slight differences in terms of what people might say, in terms of the way they sort of think about this taxonomy. Hold on. But the first model is what's called a configural model. That's our unconstrained model. Then I can constrain all the factor loadings to be equal. And now if I constrain all the factor loadings to be equal and the fit is way worse, then I could consider looking at a partial metric invariance model where I look at I constrain some, but not all of the factor loadings to vary across groups. Again, from an informational perspective, I think it's good to know like which are the items that where you can't constrain those loadings to be equal across the two groups. What you're going to do with it eventually, I mean, that's a whole nother ball of wax that we won't get into right now. If I can constrain the loadings to be equal, then I can go to a scalar model where I can constrain the intercepts to be equal. And again, I've said, do not constrain the intercepts for variables with unconstrained factor loadings. We're never going to constrain intercepts for variables with unconstrained factor loadings. Okay. Again, if the fit of model 3 is worse than 2, we might explore a partial scalar invariance model. But let's assume we get through steps 2 and 3. Then we can constrain the measurement errors and the covariances among the measurement errors to be equal. Here's another point. You would never constrain the covariance between two measurement errors to be equal if you didn't constrain the variances. Why? Why wouldn't I constrain the covariance between measurement errors to be equal if I don't constrain the variances to be equal? I mean, it doesn't make sense to me anyway. But why do you think it doesn't make sense to me? Well, though constraining the error variance to be equal just means that those, right, the error variances are still totally different, right? This is the unexplained piece of this, the unexplained piece of this. Well, think about it up here. Why might I not want to constrain this? Why might I not think you would? Well, let's say that you think, I mean, if you constrain a covariance to be equal without constraining the variances to be equal, then you're actually constraining the correlation to be different. Because remember, the correlation is a standardized covariance. And so if you constrain the covariance to be equal, but you have the variances are different, then you're basically constraining the correlation between the two variables to be different from each other. You see what I'm saying? Usually we're interested in like, what's the degree of relationship? And like, it just seems very weird to, if you constrain the variances to be equal and you constrain the covariances, then you're also constraining the correlation to be equal because the variances are equal. So, you know, if the variances are equal, to be equal across the two groups then you're actually constraining the correlation to be equal. But if you constrain the covariances to be equal without constraining the variances to be equal, you haven't necessarily really, I would argue, you haven't really accomplished anything, right? So I personally don't think it makes sense to really constrain. If you're going to if you really want to constrain those covariances to be equal, then that's a place where it really makes sense to constrain the error variances to be equal and the covariances to be equal. It doesn't, to me, tell you much of anything if you say, I've constrained the covariances to be equal, but if the variances are very different, then what does that really mean? Is the covariance, you know what I'm saying? Does that make, do you follow me? Okay. So, and then finally, you might want to constrain the factor means to be equal and the factor variances and covariances to be equal. And I put little stars there because, you know, like steps 5 and 6 you could do in the opposite order. You could do them concurrently. Doesn't really matter. I think steps 1 through 4 follow very logically, and then it's after that that you would look at. But you know, first or the variances first, or look at them simultaneously. That's really up to you. Yeah, I mean, if you have a correlation between measurement errors, then yeah, if that's part of your model, it would be there. You're just not constraining it. But yeah, so So what I'm saying is you wouldn't do anything about constraining covariances among measurement errors until, I normally would not do anything with covariances among measurement errors until step 4. And I do that along with constraining the variances of those errors to be equal. Yeah, that's good. Well, this was that longitudinal invariance example, but like if there's and actually in the example that we do, there is an error covariance. There's a covariance because we're going to use that same SAS data that we used way back earlier in the semester. And we did allow for one error covariance between two items. You would have that error covariance in all of the models. You just wouldn't make any constraints on it until step 4. So it's not like it's, you're starting with whatever is your best model from the single group case. Like, so this is, so if the model has error covariances in it, it has those error covariances. You're just not making any constraints on those error covariances until step 4. Okay, so I think this is actually a good place for a break. Let's come back in about 10 minutes, and then I will show you how to do all of this in M+ and interpret the results.
I've got time for 2 questions. I don't think it takes more than.
Yeah, I'm gonna have to run home pretty quickly after, but 5 minutes is fine. Yeah. Okay, so let's get back to work. Okay, we talked about the taxonomy of models. Let's see if there's anything I want to say. Okay, so in terms of step one, I mean, obviously, before you ever get to the multiple group step, you really should make sure that you have a good fitting model, right? So there's some, again, this is sort of work that you're going to do after you've already done a lot of work. When we fit this unconstrained model, what's called the configural model, which again, we're making some constraints. We're making the constraints we need to identify the model. But when we fit this unconstrained model, it actually works out to be the same as if you were to separately fit this model across the two groups. So, you're going to run this model. You're going to get a chi-square, right? If you were to actually run this model separately across the two groups, you could actually take the sum of the chi-squares for those two single groups. So like I run it for boys, right? I get a chi-square. I run it for girls. I get a chi-square. You could actually sum the chi-squares from those two separate models and sum the degrees of freedom from those two separate models. And that is actually going to give you the chi-square and degrees of freedom for this model. So it is like you're not separately estimating the two models, you're jointly estimating them, but you're jointly estimating them as unconstrained as they can be. So it's basically like the same as if you were to literally run it separately for the two groups. Yeah. Oh, sorry. Okay. So, and obviously, because this is an unconstrained model, it ought to fit well, right? So this is the least constrained model you're fitting. So if this model fit is not good, it's only going to get worse as you make those increasing constraints, which is why I say you got to do some work before you get here, right? This isn't you know, you don't start out with a multiple group CFA. Usually, usually you start out with a regular, right? Like this is, all of these things happen in a research process, right? It's not necessarily the same sample, but like you've done work, you've created this model, you created an instrument, let's say, you ran an EFA, you collected more data, you ran a CFA, you collect more data, and you're doing this multiple groups invariance study. So like this is, we're along a path. But again, like if step one is bad, that puts an upper limit on how good anything else can look. Now, the other thing that I will say is I find, again, I find it really helpful to look at the parameter estimates from step one, because remember, in step two, I'm going to constrain all of the loadings to be equal. So I like to look at the loadings from step one because they're not constrained to be equal except for where they have to be for identification. I like to look at the loadings from step one because I can get a sense of, is it going to be reasonable to constrain these to be equal? They're never going to be identical across the two groups, in the unconstrained model, but they should be, if they look pretty close, that's good, right? They should look really pretty similar. If they look wildly different, like the loading is 0.2 in one group and 0.8 in the other group, right? Then, I know before I go to step two that, when I constrain that loading to be equal across the two groups, it's not going to work well, right? So you can get a real sense from the unconstrained model whether making those constraints is going to work, because the parameter estimates should look similar across the two groups in the unconstrained parts if you're going to be able to constrain those parts successfully. And if they look really different, that's going to suggest to you that you can't, right? Or maybe you picked the wrong marker variable. That's also something else to think about. All right. And again, we've talked about invariance of factor loadings. We've talked about invariance of, the equality of the indicator intercepts, the scalar models. And we've talked, I think, about the equality of residual variances. I'm just looking to see if there's anything on here that I haven't said already. I feel like I've said all of this. Okay. And then again, equality of the factor means and variances, I think, are often conceptually some of the most interesting questions, right? Yeah, okay. Feel like we've said all of this. Okay, so potential issues. Obviously, things are getting increasingly complex. We've got more output. We've got more things to look at. Especially like, as I said, you're going to get a lot more output. So the sheer size of the output can be a little bit overwhelming, especially if you combine it with bootstrapping, although you don't necessarily need to. Like for these measurement invariance models, there's no reason to do bootstrapping. Remember, bootstrapping is something we want to do when we're testing indirect effects. So when we're doing the multiple group SEM stuff next week, that's where the bootstrapping might be more important. And again, we need large samples. We need whatever group to have a decent sized sample, and we need to start out with a model that fits well. Okay. So here's our multiple groups SEM model that we're going to look at today and next week. But again, today we're just going to do the measurement model. So next week we'll do the structural model. So here's what our measurement model looks like. And, remember that we talked about in our measurement model, we have these two observed variables that aren't actually factors. And I've put them into the measurement model here, and they're just correlated with our other three factors. We've got a correlation between the errors of items 20 and 29, which again sort of was suggested in our single group analysis. And so this is the measurement model that we're going to fit, and we're going to look at between group differences. We're going to look at boys versus girls for this model. So if you run a multiple, this is important to say. Okay, so you run a multiple groups model in M+. And this is where the defaults kind of get a little wonky. All groups are constrained to have equal loadings and equal intercepts by default. So the default model in M+, if you just sort of say you're going to run a multiple groups model, is going to be the scalar model. But you can override this, and obviously you'll want to. I'm sort of suggesting that you go from the least constrained model to the most constrained model. So the scalar model is kind of like your step 3 model. So you're going to need to relax some of those constraints for steps 1 and 2. Different software packages work differently, by the way. So some software packages have like the default model be the least constrained model, the configural model. That's not the case in M+. There's also a nice little shortcut in M+ that you can use with a caveat. There's a shortcut that will give you the configural metric and scalar models all together, and it'll give you chi-square difference testing and all kinds of stuff. It's really nice little trick. But it only works for pure CFA models. So the model that I just showed you that I want to fit, because, hold on. Because, where to go? I'm going. There we go. Because I have homework and GPA in this model, I can't use the shortcut, the M+ shortcut. It won't run. If I want, I could run the M+ shortcut if I just had the 3 latent variables. So it really, when I say pure CFA, I mean, no, just a CFA without any like observed variables that are functioning as other conceptual variables, the way that we have this drawn. Yeah. Yeah, you can have a correlated error. That won't be a problem. You can still use the shortcut with the correlated error. It's not going to make any constraints on that correlated error, but that's okay. That's fine. Yeah, but if I tried to run this model, it wouldn't work. I'd have to take out GPA and old. So I'll show you how you can do the cookie trick. Okay. Now in our M+ code, you know how we always have a model, right? So model describes the overall analysis model. But we can also, now because we're going to have 2 groups, we'll have like another model statement that'll say model and then whatever the name of the second group is. So like we have model, let's say, our overall model, and then we'd have like model female or whatever, if that's our second model. And then what you're going to do in that model, actually, if you look at the output, you should all have output in front of you, right? Take a look at the output that says multiple groups, CFA model, scalar model. This is the M+ default. Maybe that's not the best one to look at. Hold on. Okay. Turn to model 2. Let's go all the way back. Turn to model 3. Which is on page, hold on, 23. Thank you. If you look at page 23, model 3 is the configural model. Both the loadings and intercepts vary. So this is the least constrained multiple groups model. So this is the model that I like to start with. Here we go. So if you look at this model, notice that I have, variable names are, use variables, fine. Next thing that you'll notice that's different in this syntax is there's something that says grouping is. And that's the grouping variable. So I'm going to tell it what the grouping variable is. And I do that in the variables command. It says grouping is sex. And then in parentheses, I just put what the number, because remember, M+ always has to have numbers, right? I'm not going to have male and female in the actual data file. So 0 equals male, 1 equals female, which is helpful. If you put that in there, then it will actually label stuff, male and female for you, which is nice. Okay, so grouping is sex, 0 equals male, 1 equals female. Fine. By the way, this analysis line, somebody asked me about this for last time's homework, where I say iterations equals 10,000. You don't ever have to put that in any of the homeworks that I give you, but this just sets, the number of iterations is set by 1,000 by default in M+. Occasionally, you can bump up the number of iterations, and it'll just, if it gets to the end of the number, if it's 1,000 iterations and it gets to 1,000 iterations and it hasn't converged, then you'll get that non-convergent solution thing. So, sometimes it helps to up the number of iterations, but honestly, usually it doesn't. Usually if it doesn't converge in 1,000 iterations, it's not going to converge in 100,000 iterations, but that's another story. Anyway, but you don't really need that, but it's in there. You can see the little thing that I blanked out is actually, that's just that shortcut thing that I was talking about, but forget about that. So, okay, so now we've got model, and I'm reminding you factor loadings are going to be set equal by default in M+. So the scalar model is the default model in M+. So I'm going to have to tell M+ for this configural model that I want to loosen those constraints. So, okay, so here's my model. I just say, right, academic self-concept is measured by these 3 variables. Goal, evaluation, motivation are measured by those other 3 variables. I'm correlating homework and GPA with my latent variables and with each other. I don't think I say that, but oh yeah, I do. I do say that. I was going to say it's going to happen anyway. And then intercepts, remember, happen in square brackets. So when I just list all of those items in square brackets, those are the intercepts, which are going to be held equal by default. I have that correlated error of S20 with S29, and I've just put it in a note if that's not held equal but constant by default. And then academic self-concept, goals, and motivation, those are the latent variable variances. Those are freely estimated across the 2 groups. Okay, and the academic self-concept, goals, and motivation, by default in M+, the means in the reference groups are going to be 0, and they're going to be freely estimated in the other group. Okay, yeah. No, not between each other, between groups. Oh, no. No, never between each other, between groups. So if I were to run the model, if I just, everything up until where it says model female, if I were just to run that, it would give me the scalar model, because by default, it's going to constrain the factor loadings to be equal across the groups. It's going to constrain the intercepts to be equal across the groups. It's not going to constrain the error variances or covariances to be equal across the groups. It's not going to constrain the factor variances to be equal across the groups. Okay? Yeah. So what I need to do to run the configural model is where it says model female, what I'm going to put in these statements are the things that I want to allow to vary across the 2 groups. So notice that so I say model female colon, and again, I don't have to repeat the whole model. If I don't want anything to freely vary across the 2 groups that's constrained, I could put nothing in there, but I do. So I say academic self-concept by S13 and S20. Why don't I say S11? Yeah, it's the marker variable, right? So so the marker variable obviously is not going to be free to vary across the 2 groups. It's constrained to be 1, right? But I am going to allow the loadings for S13 and S20 to vary. So I say that. I say goal by S25 and S29. Again, it's just the 2 non-marker variables. And motivation by S26 and S35. And so by putting those down here in model female, I'm saying, hey, estimate those parameters separately for females. Follow? And then, remember I said the item intercepts are actually held equal by default. So for the configural model, I want the item intercepts to be freely estimated. So I'm putting those down there too. Okay? S13, S20, S25, S29, S26, and S35. Now I didn't put in the marker intercepts. And I didn't put in the marker intercepts. What I'm doing here is I haven't constrained the marker intercept in either group. I mean, I haven't constrained the marker intercept to be 0. You know, I said you could constrain the marker intercept to be like 0 in both groups, and you could then freely estimate the factor means in both groups. I'm not doing that. I'm going to I have the factor mean by default in M+ is going to be constrained to be 0 in one group, and it's going to be freely estimated in the other group. And I didn't put the marker variables in this list. Do you notice that? So what that means is that M+ is going to constrain those intercepts to be equal to each other. And that makes one constraint. And the other constraint is that I'm constraining the factor mean in the second group to be equal to 0. That's a second constraint. And that gets me to 8 pieces of mean and intercept information. Well, it's not in the code, but it's by default, M+ is going to fix the latent mean for the first latent variable to be 0. And it's going to freely estimate the latent mean for the second, I shouldn't say first latent variable. Latent variable in the first group is going to be fixed to be equal to 0. And in the second group, it's going to be freely estimated. Yeah. I tell you that so that you know that, yeah, but you don't really see it in the code, but by default, the means in the reference groups are going to be 0. And we'll see that, we'll actually see that in the output. Okay, so I don't do anything with the marker. So basically the marker intercepts and the marker loadings don't show up in this model female, right? But the other intercepts and loadings, I'm now allowing to freely vary across the groups. And that's it. That's how you do it. I know it's a little confusing, right? Because the thing that's weird, and that's why I never know which ones to present first or last, because like the defaults are actually what I would argue is, what to me seems like model, the scalar model seems like the most constrained model. Okay, so let's take a look at, I don't even know that we really need to run it because you've got everything here in the output. So let's take a look at this. Let's keep looking at this output so that we can see what this looks like. Okay, so, and let's keep track of our chi-square too. So we've got our chi-square is 89. 70 degrees. Keep track of that for a second. The model fit indices look pretty good. They 0.993 CFI, 0.03 RMSEA. You see the chi-square contribution from each group. This is kind of nice. So that 89.619 breaks into basically a chi-square contribution of 54.956 from the males and 34.663 from the females. Now be careful about that because remember, chi-square is a function of sample size. So like if you've got way more males than females, then of course the chi-square contribution would be bigger for males than females. You know what I mean? So like this can be really, if the groups are approximately the same size and one of the chi-square contributions is really big, then that would actually mean that the model fits less well for that one group. But it could just be a function of the sample size of the two groups. And I forget, let's see. I think it says how big our two groups are, but I forget how big they are. Let's see. Actually, it's probably on the first page. Can't remember if they're similar or not similar. Okay, so now that's interesting. What'd you say? 249 male, 370 female. Now that's interesting because actually there are way more females than males, but the chi-square contribution from male is larger. So actually, this model does fit worse for males than females, right? The model fit is, but again, without looking at, really need to know what the sample sizes are to sort of know that that's the case. All right, next thing. Okay, so we get our unstandardized factor loadings and, for males and for females. So, take a look and you can see, like, for example, academic self-concept by S11 is our marker variable. So of course that's constrained to be equal to 1. S13, you can see that the unstandardized factor loading is 0.98 for males. And it is, I just saw it, 1.044 for females, right? Do you see that? S20, it's 0.922, the factor loading for males. It's 0.985 for females. These are, again, not the same, but not like drastically different either. Goal valuation, if you look at males and females. Now they're a little bit more different. Do you notice that the goal valuation S25 and S29 are, they look a bit higher for females than for males. Do you see that? They're like about 1 for males, about 1.3 something for females. Again, like, how is this going to translate into constraining them to be equal? We'll see when we do metric invariance. But okay, so we've got all that good stuff, right? Fine. Let's look at the means. Yeah. So these are just the unstandardized factor loadings for males and females, right? And at this point, I'm just kind of looking to see if they look similar to each other. I would probably interpret this. Yeah, I'd probably interpret later after I figure out if I can constrain them to be equal or not, and I'd probably be more interested in looking at the standardized loadings for interpretation purposes. But remember, it's the unstandardized ones that we're constraining to be equal. So right now, my big interest is just kind of like, this is what I would do. I'm eyeballing all of these things that I've allowed to freely vary to say to myself, okay, I'm about to go to the metric model. Do I think it's going to work? If it doesn't work, where do I think it might not work? And again, if everything looked really wonky, I might wonder about my marker variables, but I don't see that here. Okay, so let's look though at the means. So look at the means for male, for ASC, goal, and motivation. Remember, those are our 3 latent variables. Yes, Hannah. Mm-hmm. Yeah, that is true. That's still going to be true here. For the means and intercepts, we're still going to be looking at the unstandardized output. You don't really want to look at means and intercepts from the standardized. That is true. And so now now I do want to actually interpret the means from this unstandardized. So I want you to take a look at this. So remember, GPA and homework, they're just observed variables. So these, like, they're not constrained in either group. So you can see the mean GPA is like 5.7 for males and whatever it is for females. But look at academic ASC, goal, and motivation. Those 3 latent variables. Notice that in this male group, all of them have means of exactly 0, right? And then also notice that you don't get a p-value and you don't get any kind of critical ratio or walled test, right? That's because, remember what I said, by default, M+ is constraining the means to be 0 for the latent variables in the first group. Now let's look at the means, though, for the second group, okay? So for the second group, the means are, let's see, we're on page 27, okay, where it says means. And notice this, academic self-concept, the mean is negative 0.089. Does everybody see that? So what does that mean? That really means that's the difference between males and females, and it's negative, and females are 1. So what that means is that females' latent mean is 0.09 lower than males on academic self-concept. But is that statistically significantly different from 0? No. And so this is what I was talking about, like the sort of our latent mean t-test. So that 0.413 tells me, okay, so the difference between males and females on academic self-concept is not statistically significant. Again, for this unconstrained, we haven't done all of the measurement and variance constraint stuff yet, which we really should do before we look too much at the means, but I just want you to see how this works with the defaults. And then goal, this is interesting. So now for goal valuation, females are scoring 0.3 points, or again, shouldn't say score, it's latent. The latent mean for females is 0.3 higher than the latent mean for males. And that is statistically significant. The p-value is 0.001. So what I can say here is girls and boys, so far I can say girls and boys look similar in terms of their academic self-concept. Girls have higher goal valuation, which means they seem to value the goals of school more than boys. And then the last one is last one, motivation. So motivation, and where I just lost my spot here. Oh yeah, 0.289, and that's also statistically significant. So girls are also 0.29. You know, their motivation is 0.29 higher than boys. So that is, you know, also statistically significant. Now you might be saying to yourself, well, it's a t-test. So what about something like a Cohen's d? Absolutely. You can do that. How would you do it? Okay, the Cohen's d is always the difference between the two means in the numerator. And the difference between the two means in the numerator, that's this, right? This would be the numerator. You just take this number and you put it in the numerator because it's already the difference between the two means. What are you going to put in the denominator? Well, how do we compute a standardized, effect size? The standard, yeah. So what should we use? We should use, again, there are different ways different standardizers you can use, but often a really common one would be to use the pooled standard deviation, right? The pooled standard deviation of what? Of these two groups on the latent variable. So remember, we have latent variable variances here. So our latent variable variances are, got to find those. They're here somewhere. Let's say goal. Let's use goal. So for goal, it's 0.966, right? For male. And for goal, it's 0.413 for female. Does everybody see that? No? Okay. So page 25. Oh, wait a minute. Page 26 when we get to variances. Sorry. Page 26 where it says variances. These are the variances for males. Does everybody see 0.966 is the variance for males for goal? Got it? Now, what's the variance for female for goals? Now I'm going to go over to the female page, and that's on page 27, where it says variances and look at goals. The variance for females is 0.413. Does everybody see that? So first thing that's interesting here is, wow, there's a lot more variance in terms of valuing the goals of school for boys than there is for girls. So that's kind of interesting. So like girls are much more homogeneous, and it turns out they're higher too. So which we saw because the latent mean was 0.3 higher. So they're much more, they have more goal, they value the school goals of school more, and they're more homogeneous as a group. So girls tend to be high and similar to each other. That's what this is telling me. Boys tend to be a bit lower and more variable. Now, to get the actual pooled standard deviation, I would want to take the variance of group 1, you multiply that by the sample size of group 1 minus 1, I think, right? Plus, so it'd be like plus the variance for group 2 multiplied by the sample size of group 2 minus 1. The point here is that we need to weight those variances by the sample size to get the pooled standard deviation. Once you've done that, you add those together and you take the square root. The point is, you don't know that formula off the top of your head. Just use the formula for the pooled standard deviation for a Cohen's d. But in place of like observed variances, you're just plugging in the latent variable variances for the two groups. So there's really nothing new here. We can just use that same logic. And if you do that, I don't remember what the effect size is going to be, but it's going to be pretty big actually, because we've got more girls than boys, right? And the variance is actually smaller for girls than boys. So I think it works out to be more than half a standard deviation unit. You could do it out. I should do it out. But anyway, that's how you compute the Cohen's d. Maybe I did it for the scalar model. I don't know. All right. So is everybody with me on the, that makes sense so far? With me? Okay. So now let's go to the metric model. Should we do it? Should we pull it up in M+? You want to do it? Not do it? I don't know if it really matters. It's nice to have it on the board though, I guess. So I will do it quickly so we have it on the board in case we want to look at it. Open. Oh, especially for people who might be at home, who have nothing to see. I don't think anybody's at home, but when you're watching this later. Okay, hold on. So desktop, week 10. So now we're going to do the metric model. Let me make this bigger. View, no, not view. Edit, change font, choose font. 18 is probably good. Go. Okay, so now the metric model. So here's the metric model. Nothing has really changed except, remember with the metric model, now I want to constrain the loadings to be equal across the two groups. So what am I going to take out of the code from the last model that we just looked at? So model 2, by the way, in our output is going to be page 13. Thank you. Yes, page 13. So if you look at the code here, again, this whole top model code stays the same. But in model female, look what I did. Because this is the metric model, I'm allowing the intercepts to vary across the two groups, but I'm constraining the loadings to be equal across the two groups, right? And so what I did is I took out all of those by statements from model female. Because, again, this is where it's really important to know what M plus's defaults are, because by default, M plus is going to fit the scalar model, and I'm always going to put in this model, whatever the model is for group 2, I'm going to put the things in that I want to allow to freely vary across the two groups. In terms of the loadings and the intercepts, those are the things that are going to be constrained by default. So remember in the configural model, I had those 3 by statements with I took those out because now I want the loadings to be equal across the two groups. But I leave in the intercepts, the 6 intercepts that I want to constrain to be equal across. Wait a minute. No, I'm sorry. I leave in the 6 intercepts I want to be free to vary across the two groups. I take out the loadings that I am constraining across the two groups, right? Showing something here means it's free to vary. That's right. In terms of loadings and in terms of intercepts. So if it's in here, I'm allowing it to freely vary. So the scalar model is the default model. So when we get to the scalar model, we won't have anything in model female and then we'll be constraining the loadings and the intercepts to be equal across the two groups. Here, I'm allowing the intercepts to freely vary across the two groups. So they're still in model female, but I'm constraining the loadings. So they're not. I know it seems backward. I get that. Like it feels like it should be the opposite, but it's not. So you'll get used to it eventually. And again, that's the way it works in M+, but there's no guarantee that, different SEM programs work differently. So some programs have like the unconstrained model as the default, and then you have to make constraints. This makes the scalar model the default, and you have to like work to unconstrained things. Was there a question? Yeah, we're going to look at the unstandardized. Yeah, and we're going to look at the model fit most of all. But yes, we're going to look at the unstandardized results. But they're going to be the same once we constrain them to be equal. So they will look the same, because whether it's a reasonable assumption or not, because I've constrained them, they will be equal across the two groups. So it's going to be really important to look at the model fit, because when you look at the loadings in the metric model, the unstandardized loadings will guaranteed be equal across the two groups, whether they should be or not, because you've made it so. Do you know what I mean? So that's where the model fit's going to be super important. Well, yeah, we haven't looked at that yet, but so let's run our model. Take a look. Okay, hold on. Let me change my font here to 18 point. Sure, that sounds good. Okay. Okay, so now this is my metric model. Take a look at our chi-square, blah, blah, blah. Where's my chi-square? Did I miss it? Here we go. So my chi-square is now 100. 0.78, right? With 76 degrees of So I could do a chi-square difference test here, right? I've picked up 6 degrees of freedom. What are those 6 degrees of freedom? Yeah, the 6 factor loadings that are now constrained to be equal across the two groups, right? And if I look at this, I think I get 11.16 chi-square difference. 11.16 with 6 degrees of freedom. Oh, I don't know what the chi-square critical is with 6 degrees of freedom, but I think I probably wrote it in here somewhere. So let's see. You're right, 12.592, because I did write it in here. Yay. Okay, so the chi-square critical with 6 degrees of freedom is 12.592. And the chi-square difference here is actually less than 12.592, which means that the fit of the metric invariance model is not statistically significantly worse than the fit of the configural model, which means I can make these constraints, right? I made these 6 constraints and my chi-square didn't go up by that much. So I'm good. So yay, metric model. So I can do it. Okay, so I favor the metric model here. Does that make sense to everybody? Okay, so the next step is going to be the scalar model. So to fit the scalar model is going to be really easy, because to fit the scalar model, I can basically just take out this line, right? Once I take out the line that's referring to the intercepts for female and allowing those to vary, then I'm going to get the scalar model. And again, the scalar model is the default model. So if I take that out, I could just like get rid of it, right? Then this should give me actually, this will give me the scalar model. Changes though. So here's my scalar model. How many degrees of freedom am I going to have in my scalar model? Uh-oh, I didn't save my changes. I guess it doesn't work to not save them. All right, lesson learned. I don't know why I care, but scalar model. Okay, run my scalar model. There we go. So here we go. Chi-square. Go. There we go. Chi-square. Yeah. Oh, no, because that's the difference between the scalar and the metric. You're going to see. Yeah, so yeah, that 14.6. So now we've got 115.427 with 82 degrees of freedom. So we picked up another 6 degrees of freedom because there are those 6 intercepts that we've now constrained to be equal. Point. Call it. Now, if you look at 115 minus 100.78, that equals 14.65. So that actually means, again, that is statistically significant, right? So which model would we favor? The metric model, right? But now the thing that we don't know here is, could it be, and this is where partial invariance would come into play. So what we know is by making those 6 constraints, the chi-square went up by 14.65 points. But it's very possible that most of that chi-square increase could just be one of the 6 constraints that we made, right? That's very possible. It's not necessary. Like, it could be that all of them are it could be equally distributed in this fit across the 6 intercepts. And so, like, each of the 6 intercepts sort of contributes equally to that chi-square difference. But it also could be that, like, it's really one of the 6 intercepts that's problematic. So if I wanted to get a sense of that, I could compare the intercepts, but I can't compare the intercepts from the scalar model because they're constrained to be equal. So I'm not going to see anything there. I'd want to go back to the metric model and look at the intercepts from the metric model and say, do any of the intercepts from the metric model look really different from each other? So let's do that actually. Let's take a look. So going back to the metric model and looking at our intercepts, unstandardized, that's correct. And I've kind of marked what the markers are. So that's right. So page 16 versus page, there we go, versus page 18. So you can kind of fold over a little bit and take a look and let's see. So like S13 is 4.8 for male, which group is which? Males are group 1, right? 4.8 for males and 4.78 for females. That seems really similar, right? Okay, I'm skipping the markers for now. S20, 5.02 for males, 5.12 for females. That doesn't really seem too different, does it? Next one, 6.2 for males versus 6.11 for females. That doesn't seem that different. 4.988 versus 5.277. Okay, that feels a little bit more different, doesn't it? No? 0.3, yeah, but that's a lot more than 0.05 or 0.07 or whatever. I'm just saying, out of all of them, that is certainly the biggest difference. Again, part of the difference, you'd want to think about the standard deviation units too, like because 0.3 might be big or might be small, depending on what the variance is in that particular item. But I'm just saying, so far that certainly looks like the biggest difference. 6.104 versus 6.105, they're virtually identical. And 5.133 versus 5.054, those are very similar as well. So, I mean, again, eyeballing it and without looking really at the standard deviations, but I could look at, let's see, it's S25. Was that the one? 26, thank you. S26. S26. So let's look at the variance for S26. We have that information here somewhere, right? We can just look at the sample statistics. So let's see, the variance for S26 is 2.767 for males. And for females, it is 1.974. So you have to take the square root of those to kind of think about the standard deviation. So the standard deviations are probably like 1 point. Oh, sorry, pages 3 and 4 of the output where the sample, I'm just looking at the sample statistics for the covariances and variances, right? To get an idea of what the standard deviation would be. I mean, it's not a huge difference. I mean, the standard deviations are over 1, and it's like about a 0.3 difference. So, probably about a 0.2 standard deviation unit difference between the two groups in terms of that intercept. So it's not like enormous. It certainly is the biggest of the differences that we saw in the intercept. So just for laughs, yes. Oh, I was just looking at the variances of S26 for males and females. So if you look on page 3 at the covariance matrix for S26, the diagonal for S26 is going to be the variance of S26. So 2.767 is the variance of S26 for males. Have to take the square root of that to get the standard deviation, right? So what's the square root of 2 points? Hey, I think I brought my calculator for just this kind of occasion. Let's see here. Okay, so take this 2 points. Hold on, let me do square root first. Oh, I definitely need my reading glasses. Hold on. 2.76 something. Okay. Okay, so the standard deviation for females or males, which one's first? Males is 1.66. Now, if I go to the next page for females, I think it's on page 4, S26, 1.974, if I take the square root of that, 1.4. The standard deviation is 1.4. What did I say the other one was? 1.6 something? So let's call it around 1.5, shall we? And we see a 0.3 difference. Let's call the approximate average standard deviation. Of course, I'm just like I'm just like spitballing here. I'm not actually doing the pooled standard deviation, but it would get me close, about 1.5. So 0.3 divided by 1.5 gives me 0.2, right? So that means in standard deviation units, there's about a 0.2 standard deviation unit difference between males and females in terms of that item, the intercept of that item, which is, again, control. Remember, the intercept is, controlling for the factor, right? So I don't know, is that big? Yeah, I was going to say, like, it's probably big enough to wreak havoc with my measurement invariance. It's not huge, but it's probably big enough. So what I can do here is I can test this, right? So what I can do is I can just free the intercept for that one item, and I can see what the chi-square will be for that, right? So let's do it. So, okay, so I've got my scalar invariance thing here, and now I want to go into my model. Do I have model female? No, model female, but that's okay. So now I'm going to say model female. Colon, and don't let it throw you. You'll notice that it doesn't get blue like the model colon statement does, but that's okay. It doesn't, don't worry about it. And it was S26, right? Yep, S26. And it's the intercept of S26. So
Female, there's an I.
Oh yeah, that's totally gonna mess me up. Let me fix that in a sec. Thank you. Okay, so it's S26 in brackets. If you don't put it in brackets, then it's gonna think you're talking about variances, which it's already not, error variances, which it's already not constraining, so it really won't do anything. Okay, so model female, S26. So again, now we're gonna allow the intercept for S26 to vary across groups. How many degrees of freedom are we gonna have for this model we're about to run? Yeah, 81 degrees of freedom, right? So let's see how this goes. Okay. Save. Run. Well, this is so exciting. Here we go. 81 degrees of freedom. Okay, here we go. 81 degrees of freedom. And the chi-square is 104.39. Now, at 115 or 3 minus, what did I just say? So we get, right, chi-square difference of 11.12, 1 degree of freedom. Which is, yeah, which I was going to say. So right now, this is statistically better than the scalar model, right? So this partial invariance model is better than the scalar model. And this model, we can now compare to the 100.78, which I'm talking about. So we can take 100.78 and compare it to the 104.31. And but I think that's right. 3.53 with how many degrees of freedom? Comparing it to the metric model? 5, right? Because we still are making 5 additional constraints, 5 intercepts. So with 5 degrees of freedom, this isn't even close to. So what this says to me is like, okay, out of those 6 constraints I made to go from the metric model to the scalar model, 5 of the 6 constraints I could make and only increase the chi-square by about 3.5, which is like nothing for 5 constraints, right? One of those 6 constraints, though, that S26 constraint, actually contributed out of that total of 14.5 chi-square points, contributed 11.12 of that total. So it was just one of those constraints that was really driving the boat in terms of not being able to impose scalar invariance. So what I could do is I could stick with this model, and this would be what's called a partial scalar invariant model, right? Where I'm able to constrain all of the factor loadings and all but one of the intercepts to be invariant. Does that make sense? Yeah? You follow the logic? Mm-hmm. Well, yeah, probably. Yeah, marginal. I mean, barely, right? 104.309 was the metric. What was the metric? What the metric? Not that it really matters, but okay, the metric was, yeah, 0.03, right? And the configural was, I think the configural was, oh, so technically the configural had a chi-square of 0.057. But I mean, I think we're just, again, I think the more important point here is not where do you cross the threshold from statistical significance to non-statistical significance, but really sort of in the march of models, is my, am I sacrificing model fit? Like, yeah, okay, it's a 0.04 and it was a 0.05. Is that meaningfully different? No, only because somebody's told you that 0.05 is some magical threshold, but in reality, there's really no difference. Oh, you mean to keep going down the, yeah. I mean, you could keep going down the taxonomy with partial scalar invariance, start looking at the error variances. Like, would you want to constrain the error variances for S26 to be equal? Probably not, but you could potentially constrain the error variances for the others. And I say probably not for two reasons. One, I mean, I just think, doesn't always make sense to make more stringent constraints, but error variances are a little different. So, but the other reason that I say probably not is because when we were looking at the variances, the variance for males and females on that variable was pretty different. Remember, it was like forget what they were now, but the variance was a lot bigger for males than it was for females. And if the variance of that item is a lot bigger for males than females, then constraining the error variances to be equal is sort of unlikely to work, So, I mean, my guess is I wouldn't expect to be able to constrain the error variance for that item to be equal, but you could potentially try to constrain the other 5 error variances to be equal. Okay, so other questions. Does this make sense? So, time is it? 12:03. Okay, so I did want to talk briefly about this continuous censored and count variables handout that I gave you. So again, this quickie, if you're only doing a CFA, so you don't have, if we hadn't had homework and GPA in there, we could run this model, and that's what I've done here. So let me pull this up. Shortcut, here it is. So if I just want to run configural, metric, and scalar invariance models, and I just want to do it all in one step, and I want to get the chi-square difference testing and everything, and I don't have GPA and homework in here anymore, I can do that really easily with this little Jiffy shortcut. So I've given you a handout about this. And you can see the line. Now I don't have model female anymore. But what I do have, oh, I've lost my cursor. Where are you, cursor? there we go, I have this line that says model, configural, metric, and scalar. And so I'm telling it to estimate the configural, metric, and scalar models. And it's going to do so, it's going to run through. And here, I'll show you. Really nice. I mean, it's really nice. It didn't used to exist here. Really appreciate it. Okay, so I run it, and you'll see that, okay, it runs. It'll tell you, it says, okay, here's the configural model. Now this is going to look different because I've taken out GPA and homework. So that's why these chi-squares and degrees of freedom are not the same. But I've got, okay, so for the configural model, I've got a chi-square of 60.376 with 46 degrees of freedom. P-value is 0.078. Okay, great. Things look pretty good, right? Now let's go to the, go down to the metric. Here's the metric model. Chi-square for that go. Oh, sorry. All the model fits are at the top. My bad. Okay, so here we go. So it's, what did I just say it was for the 60.376 with 46 degrees of freedom for the configural. The metric is 71.965 with 52 degrees of freedom. So not much of a change there. And then what do you think you're going to see for scalar? There should be a jump again, right? Because we still have this S26 problem, right? Okay, and where'd it go? Oops, scalar, 86.774 with 58 degrees. You can see we still see that same jump, right? Okay, and then we get all the results. And somewhere at the bottom here, I think, if I remember correctly. Oh, sorry. Okay, maybe it's at the top. It's somewhere here. Terminated normally. There it is. Where'd it go?
It's a nice target.
It's in here somewhere, I swear. Oh, there it is. Yeah. Oh, I think I cut out some of the sample statistics. That's why. Okay, so this is kind of nice too, because it actually gives you all of the chi-square difference testing, right? So it tells you, okay, here's the configural, metric, and scalar model. How many parameters? What's the chi-square? What are the degrees of freedom? What are the p-values for those actual models? So those p-values are just the p-values for the models themselves. And then models compared, and it gives you metric against configural. The chi-square difference is, 11.589 with 6 degrees of freedom. The p-value for that is 0.078. So we would favor metric because that's the more constrained model. Scalar against configural, you can see that chi-square difference is 26.398 with 12 degrees of freedom. That p-value is statistically significant. We would favor the configural against the scalar, right? And then scalar against metric, it's 14.809 with 6 degrees of freedom. And there we would favor the metric against the scalar, right? So it's kind of nice because it gives you all of those tables there. I don't know, kind of a nice little shortcut, but again, it doesn't always work because you can't always, do everything. Is there anything else I wanted to say? Oh, and then so in the packet that I gave you, it just explains exactly what the settings do, the configural, the metric, and the scalar setting, which we've talked about that, but I think it's really helpful to just, again, know exactly what the M+ defaults are, exactly how it's functioning. You can actually add in some partial invariant stuff here too. So you can mess with this and put in, like, if I wanted to allow S26 to vary across the groups, I can sort of combine this, but it's not as, honestly, it's not quite as flexible as just doing it the old-fashioned way. If you want to go into partial metric or partial invariance, you get more flexibility the old-fashioned way. So I think it's good to know how to do it both ways. Questions about any of that? Hey, I think we did it. I think there was only one last thing I wanted to say, which was nested models, right? Okay. So just to remind you about nested models, And there is a question, I think it's an extra credit question on the homework about nested models. But I mean, obviously, the models that we're talking about here are like the scalar, metric, and configural models are all nested models, right? That is clear. Remember that, I mean, the easiest way, there's sort of two different ways you can think about nesting. And I think the way that people usually think about nesting is sort of what, and this is really good paper, by the way, this Bentler and Satora paper that was in Psych Methods in 2010 called Testing Model, Nesting, and Equivalence, which maybe this is one of the things that got cut so far this semester. We have not done yet, but there's time, sometime this semester, we'll go back and I'll show you how to actually do all of the testing that they suggest in this model, in this paper. But in the paper, they talk about this idea of parameter nesting versus covariance matrix nesting. And parameter nesting is generally pretty easy to see, or pretty easy, generally. I mean, sometimes it's trickier, but generally it's pretty easy to think about. So parameter nesting, remember, is like two models are nested if, if I can go from model A to model B by making a series of constraints, right? Or, conversely freeing, but let's just think, if I go from a more unrestricted to a more restricted model by making a series of constraints, and those constraints could be to constrain a parameter to be equal to 0. It could be to constrain two parameters to be equal to each other. But I'm making a series of constraints, right? So I'm sort of going in one direction, from less restricted to more restricted model, again, or back again. That's really this idea of a nested model. So all of these models that we've talked about are nested, right? And how about that partial scalar model that we estimated? Is the partial scalar model is nested within the configural model, right? And it's nested within the metric model, right? It's nested within the scalar model. We're okay there, right? So, but you can sort of think about these as sort of going along a path, right? From like the least constraint would have been the configural, then we go to the metric, then we go to the partial metric, right? And then we go to the scalar model. Everybody kind of see how we're like making increasing sets of constraints on the parameters. So now, one thing about nested models is for our models to be nested, we want to have the same variance covariance matrix. So we want to have the same sample, and we want to have the same set of variables in the model. So we're not going to add or delete variables. We're just making constraints sort of in the model that we have. So that's pretty straightforward, and that really captures the nesting question that is in the homework. The reason that I hedge a lot when we talk about nesting is that there's another kind of nesting too, which is covariance matrix nesting. And this is what is trickier to see. So basically, if one of the covariance matrices is sort of nested within the other, so that, the set of possible sort of moment matrices under one is like a subset of the set of possible moment matrices from the other, then those models are nested. And just as before I'll make you even more confused, look at models 1 and 2 here. So like these models are actually nested models, even though they take a totally different format. And actually, this is an easy one to see because the model in M2 is actually just identified. So it's a completely saturated model. So the model in M1 is not, right? It makes a constraint on that. We're making a constraint where we're actually saying that the correlation between V1 and V3 after controlling for like the partial regression coefficient of V1 on V3 after controlling for V2 is 0. The direct effect is 0. So, that's a constraint that we're making there. So this is a 1DF model. And really any model is going to be constrained. Any model is actually going to be nested within a completely saturated model. If you think about it, right? Like if I make a series of constraints, if I have a completely saturated or a 0 DF model, and then I make some sort of constraints from a covariance matrix perspective, even though the model might look completely different, I actually have like a nested model there. So this is where sort of this idea of covariance nesting can be very hard to see. I mean, in some sense, it's easy if you have a completely saturated model, and in some sense, I mean, not to get too deep, but like the chi-square test is actually the difference between your model and the completely saturated model, which has a chi-square of 0 with 0 degrees of freedom. So like, in some sense, every time you run a model chi-square, you're comparing the model chi-square to a completely saturated model, which would be like a just identified model. So in some sense, any model is nested within a just identified model. Well, okay, so that's easy. So I can kind of keep track of that. But like, what if it's not a just identified model? What if it's like a not completely saturated model, right? And then I've got this other not completely saturated model. It's not always so obvious whether those two models are nested. Like it can be, because like it might not, again, they might not look like they're nested in terms of the parameters, but still in terms of the model implied moments, like they actually might be nested, which is why, with any luck, I will get to this paper and be able to show you how in M+ or any stat software package that does structural equation modeling, I'll show you a jiffy way to be able to test if any two models are nested, whether you can see them or not. So my expectations for you, for being able to see nested models, I expect you to be able to see models that, in terms of this parameter nesting, I do expect you to understand like, oh, as we, constrain parameters, right? That model with constrained parameters is nested within this unrestricted model. And I do expect you to understand that if I constrain a parameter over here, but then free something over here, then now I've like, those models aren't nested, right? Because I have, but I don't, I can't say, oh yeah, show me any two models and give me 5 seconds and I can tell you whether they're nested. I mean, I can't do that for certain models. I can do it for lots of models, but there certainly are models for which it is, without sitting down and grinding through the whole, all of the model implied variance covariance matrix stuff, it's just not totally obvious that those are nested in terms of the covariance matrix nesting. So again, so this is how you think about nested models in SEM. My expectation for you is you understand parameter nesting. I'm not going to sort of throw crazy covariance, nesting problems at you and expect you to be able to pick up on things like that. All right. Oh, and now we're over time yet again. Sorry. Okay, so let's stop there and we're almost done. I can't believe it. There is not, but I will make one. I mean, I just made this right before class, okay. So I didn't actually put it up, but I can, take one and then I'll make sure to put one up as well. Thanks for reminding me because I kind of forgot. All right, so I don't need any changes. I do need to turn off WebEx. I'm sharing my screen. Stop sharing. Stop recording.